Hi there. So right now what I'm going to talk about are sections 6.2 and 6.3 in our book, and what we're going to be discussing are antiderivatives, and we're going to talk about both definite and indefinite integrals. Don't worry, I will let you know what everything means. Okay? So the overriding question here is, suppose we know the derivative of a function, and what we want to know is there a way to get back to our original function? And the reasonable question to ask is, can we? And my answer is actually yes, at least within a constant. Okay? So, for example, suppose I tell you that the derivative of a function is 3x squared. Is there a way that I can know what the original function is? Well, I claim that one person could say, yeah, x cubed. I think you'll grant me that if you take the derivative of x cubed, you'll get to 3x squared. Now, suppose somebody else said, really? Well, I thought of the function x cubed minus 1,000. Is this also a function that would give you this derivative, assuming we called it g prime of x in this case? And my answer is yes, we actually do get back, because remember, the derivative of any constant is 0. So, for example, I could say that my original function is x cubed plus 10,000, and I would still get back to the same derivative. So the answer is yes, we can within a function. In fact, the best we can say if we're given the derivative to be 3x squared is that our original function f of x is x cubed plus c, where c is some constant. Okay? So what we want to do now is try to come up with some general procedures in order to compute these. Okay? When we talk about these things, they're called antiderivatives because we're going back from the derivative. Now, there's many techniques for computing antiderivatives. In this class, we're really going to only go through a couple of them. If you're interested in learning more techniques for computing antiderivatives, or you're going to see that another term we use is integrals, I certainly recommend you go on and take some more calculus, because certainly you can study a lot of really cool techniques. All right, so the question is then, if we can, how do we find these? Well, let's think back to our power rule. Back when we had a function x to the n, how did we take our derivative? Well, what we did is, so if this is y, then y prime is n x to the n minus 1. So you'll recall that what we did is we multiply by the exponent, and then we subtract 1 from the exponent. So if this is taking a derivative, I think you'll grant me, just on an intuitive level, taking the antiderivative means that we would take these steps and go in reverse. So what does that mean? Well, instead of subtract 1 from the exponent, what we would do is add 1 to the exponent. And then, instead of multiplying by the exponent, what you would then do is divide by that exponent. Okay, so what does this look like then in practice? Okay, at least using our power rule, why don't we write out what this would look like in general? So, in other words, if I start out with my derivative equaling x raised to some power, then the original function, f of x, well, add 1 to the exponent, that gives me n plus 1, and then instead of multiplying by that exponent, you would divide by that exponent. And you also want to put plus a constant, because remember, what we're doing is we're getting back to our original function within that constant. Now, I claim that this rule works, but not when n is -1. Because, let's look at that. If I have f prime of x to be equal to 1 over x, I claim that's equivalent to x to the -1st power. Well, what would happen if we applied this rule? Then we would get our original function to be x to the -1 plus 1 divided by -1 plus 1 plus a constant. But that would give us x to the 0 over 0, which we know is undefined. Okay? So the case when n equals -1 is a very special case. Okay? We'll get there momentarily. I just want to build to get there. Now, when we are computing these antiderivatives, we use notation for it. Okay? It's a lot quicker to use the notation than it is to write out the words find the antiderivative for. So, the notation that we use for these general antiderivatives are called indefinite integrals. And the notation for that is this. So what I would say is that the antiderivative of whatever function I'm looking at, okay, is equal to some other function plus a constant where the derivative of this function is equal to f of x. Okay? So in particular, for the antiderivative of x to the n dx, we would say that's equal to x to the n plus 1 over n plus 1 plus c. Okay? So what I want to do is go through some examples. Well, what would be the antiderivative of, say, x to the 5th dx? Well, what you do is you add 1 to the exponent, so you're going to get x to the 5 plus 1 over 5 plus 1 plus a constant. And in general, I don't show this step. I would just say it's x to the 6 over 6 plus c. Now, one nice thing about this is you can actually check your answer. How would you check your answer? Well, you would take the derivative of this, and you better get back what's inside. Okay? So, let's do that. I think you'll grant me that this is equivalent to 1/6 x to the 6th. And then we could say plus a constant. And if we took the derivative of this, well, you rewrite your constant, and then you have 6x to the 5th, and the derivative of any constant is 0. My 6's cancel, and I'm left with x to the 5th. Now, one thing that I neglected to mention earlier is, what does this dx mean? What this means is that we're computing our derivative or antiderivative with respect to x. Okay? It turns out that you can have functions of many different variables, so that's called multivariable calculus, and so you need to specify which variable you're taking the derivative with respect to, because you hold the other variables constant. Okay? That's not something we encounter in this particular course. However, we want to keep our notation consistent in case anybody does go on and take more mathematics. Okay? So, what you need to remember is this just says, hey, this is with respect to x. Okay? So, what if I asked you then, what would be the antiderivative of 7? And just to play around, let's pretend our variable is t instead. You'll see that t comes up very frequently. Well, you might wonder, how do we apply this rule? Well, I claim this is the same as 7 times t to the 0 dt, because anything raised to the 0 power is 1. So what you do is you add 1 to the exponent. So I claim you get 7t plus c. Let's take our derivative here. I think you'll grant me if we take the derivative of this function, we sure do get what's inside. Okay? Now, there's a couple properties, one of which I used already here, that are really nice because they follow directly from taking our derivative. What we have is that if you want to take the antiderivative of a sum or difference of two functions, what you do is you take that antiderivative term by term. Okay? So this just says take your derivative term by term, just like we would do with our regular derivative. The other property I'm going to mention is if you have a constant times a function, what you can do is pull your constant out and then take the antiderivative of your function, which is essentially what I did here, right? I could pull out the 7, and then what I did is I took the antiderivative of t to the 0. All right. So, what I want to do is now talk about our special case, and then I want to go through some examples here, okay? So far, what we have is the antiderivative of x to the n dx is x to the n plus 1 over n plus 1 plus c, okay? But again, remember, that's if n is not equal to negative 1. Okay, what if n is equal to negative 1? Then I claim we're in the situation 1 over x dx, right? Because if you brought your x to the top, you'd have x to the negative first power. Okay, so what we want to do is ask ourselves, do we know a function whose derivative is 1 over x? And I claim, yes, you do, the natural log function. Remember that the derivative of the natural log is 1 over x. Now you may have noticed that I included some absolute values here, and that's precisely because you can't take the log of a negative number. So whatever this is, you need to take the absolute value of it. Okay? So that's an important one. Another important one is what is the antiderivative of e to the x dx? Well, who has a derivative equal to e to the x? E to the x does. Okay? Again, you can check me by taking the derivative of what's on the right side, and you'll see that you get precisely what's on the left side. But what if now I have e to the kx dx? Okay, in other words, something like, say, e to the 2x dx. We're asking ourselves, who has a derivative equal to e to the 2x? Okay, I claim that what we're going to be doing here is the opposite of what we did when we took our derivative. Remember, when you take the derivative of something like this, what you do is you rewrite it's e raised to that power times the derivative of that power. So now what it's going to be is e raised to the power divided by the derivative of that power. So I claim in this case it's e to the 2x over 2 plus a constant. Okay? How do you know? You can check your answer. That's the same as 1/2 e to the 2x plus c. And if I take the derivative of that, I think you'd agree I'm going to get 1/2 e to the 2x times 2 using my chain rule. My 2's cancel, and I'm left with what's inside. All right, so that's part of a list. But as you can imagine, there's a few more guys that we're going to go through. Okay? So, what I'm going to do is write them all out, and then we're going to play with a bunch of different examples. Okay? So, for example, what is the antiderivative of the cosine of x dx? Well, who do we know who has a derivative equal to cosine? Sine. What if I want to do the antiderivative of the cosine of kx dx? Well, just like with our exponential function here, what we would do is we would say it's the sine of that value divided by the derivative of that. Okay? And we can do a similar thing for our antiderivative of sine. Now, who has a derivative equal to sine? Remember, the derivative of the cosine is negative sine, so we would say this is negative cosine of x plus c. And in a similar manner, the antiderivative of the sine of kx dx is negative cosine of kx over k plus our constant. Now, I understand that this is a lot. You learn these things simply by practice. So, let's go through and play with a few different examples here. All right, so why don't we compute the antiderivative of, how about x to the 6th minus 1 over 7x to the 6th dx. Okay? When you are computing these antiderivatives, what you want to do, just like when you were computing your derivatives, is bring your variables up to the top. Now, I simply cannot emphasize it enough. Do not move your constant up to the top. This is the same as minus 1/7 x to the negative 6th dx. Okay? So what that property that we looked at before told us is if we want to take the antiderivative of this, we can do it term by term. So we get x to the 7th over 7 minus 1/7. Well, what do you get when you add 1 to negative 6? I claim you get negative 5 over negative 5 plus a constant. Now, I'm not going to leave my answer like that, but that is our first step. Okay? Why do I say I'm not going to leave my answer like that? Well, I don't like negative exponents, and if I have a fraction times a fraction, you better believe I'm going to simplify that. So we get x to the 7th over 7. A negative times a negative is positive, and 7 times 5 is 35. So I claim you get plus 1 over 35x to the 5th, and then plus a constant. Now, if you don't believe it, take the derivative of this. You're going to get what's inside. Okay? All right, let's go through another one. What if I want to compute the antiderivative of, what if I have this, the square root of x minus 3 over the square root of x plus 5 over 2x plus 1 dx. All right. Now, just like with our previous example, what we want to do is first write these, bring our variables up if need be, and then also write them using fractional exponents here so we can take the antiderivative. So this is x to the 1/2 minus 3x to the negative 1/2. Now, with practice, what you're going to want to do is rewrite this term as 5/2 times 1 over x. I already know that when I see an x to the first power in my denominator, I've got that natural log. But when you're first learning this, most people would write it like this. Again, don't bring the 2 up. The 5/2 is a constant. Okay? So let's now compute our antiderivative. Remember, you're adding 1 to your exponents. Well, what happens when you add 1 to 1/2? Well, 1/2 plus 2/2 is 3/2. So you're going to get x to the 3/2 over 3/2. Don't worry, I'm totally going to clean that up. Minus 3. Okay, what do you get when you add 1 to negative 1/2? Well, negative 1/2 plus 1, which is 2/2, is a positive 1/2 over 1/2. And this guy, if you went to go take the antiderivative, you would get x to the 0 over 0, and then it's like, red alert, something's wrong, you can't divide by 0. And then you'd be like, oh yes, I remember. That's our natural log. So the way I would write this in final form is when you divide by a fraction, you multiply by the reciprocal. So I would rewrite that as 2/3 x to the 3/2 minus 6x to the 1/2 plus 5/2 log x plus c. Okay? All right, so let's just do a couple more. What if now I want to take the antiderivative of e to the 3x plus the cosine of 2x minus 5 times the sine of x dx. All right, well, term by term. And again, have those rules in front of you as you're learning these. It just takes practice to learn them. So what's the antiderivative of e to the 3x? It's e to the 3x over 3. What is the antiderivative of the cosine? Well, who has a derivative equal to cosine? Sine does. So we would say plus sine 2x over 2. This last term, I have a minus. I rewrite my number out in front. And who is a derivative equal to sine? Negative cosine. Well, negative times a negative is a positive, so I'd say plus 5 cosine x plus a constant. All right, so that should get you going in section 6.2. Thanks.